Okay, I'm going to do the third problem from our review activity now. In this problem, we have a 5 micron water droplet. If it's water, we already know its density is about 1,000 kilograms per cubic meter. And this water droplet is released in stationary air and allowed to accelerate from rest under the influence of gravity. So in class, we talked about these different cases of particle motion and the associated particle velocity profiles. And in the case then that the gas or fluid is stagnant and that the initial velocity of the particle is 0, then we had a velocity profile that looked like this. This is the terminal settling velocity, 1 minus the exponent minus time over this time scale that we called relaxation time, tau. Should say also this is for the case that our external force is gravity. So we know that this is the velocity profile that characterizes our particle, and we are interested then in the very earliest portion of its trajectory. It says calculate the velocity, so that we want v, after just 100 microseconds have elapsed. And we can assume that the Cunningham correction factor is negligible, equals 1. So in order to get the velocity, then we need both our terminal settling velocity and our relaxation time. When we looked at these velocity profiles in class, we said also that the terminal settling velocity is the product of a relaxation time tau and g, which is gravitational acceleration. And so actually, we really only need to calculate tau, and then we have everything we need. So tau is a function of our particle properties, as well as the fluid that we're sitting in. So we said the correction factor is negligible. We want to calculate the mass of our particle. So since it's a water droplet, we can do that as the product of its density and a spherical volume. And then we're in air, so we can use the viscosity of air. It's maybe important to say that we're going to assume here that this is at standard temperature and pressure so that we can use the viscosity of air at those standard conditions. So then we can proceed by plugging in. So the relaxation time will be the product of the density times the diameter squared, right? One of the diameters canceled out here. And I'm going to put the diameter in meters. Off the camera again. So the density, the diameter squared, and then in the denominator, we have 18 times the viscosity of our fluid, which in this case is air. So then our relaxation time works out to be on the order of microseconds, 7.67 times 10 to the minus 5 seconds. And we wanted to calculate the velocity then at a time of 100 microseconds. So we'll plug in this time and our tau value into the velocity profile in order to calculate v. So v after 100 microseconds is our terminal settling velocity, which is tau times g. And then 1 minus the exponent of negative time divided by tau. And now if we plug in all of those values, we should come up with a velocity of about 5.49 times times 10 to the minus 4 meters per second. This is 100 microseconds after release. A way to kind of sanity check this, right, is if we went back and we were to calculate our terminal settling velocity as the product of the relaxation time and gravity, right, VTS equals tau g equals 7.67 times 10 to the minus 5 times 9.8. Then we get a value of 7.54 times 10 to the minus 4. Right, so this is a meters per second. This is a larger velocity than what we got at 100 microseconds, and that makes sense. The particle is still accelerating 100 microseconds after release. It's converging towards this terminal settling velocity, or asymptoting towards that velocity.